All right, thank you, Hal. Yeah, okay. Well, thank you for the introduction. This is some work that I've done mainly with the folks on the left here, and you'll see a photo of a lot of them in a moment. But also some of this is inspired by some longer-term, I don't know, collaborators or maybe spirit guides over here. So there's a lot of input that went into this, however indirect. You know, they say you're supposed to open with a joke, but I had a really hard time sleeping last night. But then I realized, now if somebody asks me if I'm too woke, I can just be like, no, I never went to sleep. Okay. All right. I did want to, just briefly say a word about Keith, and Rafa kind of touched on this yesterday, but I spent a lot of time having coffee with Keith and talking about topics such as those that have been discussed already this week and which we'll discuss later. I started getting to know him around 2013, and I moved to the applied math department in 2015. Around 2016, Keith and Brad Heineman here and I, along with Jeff Vassell, wrote a solar proposal to NASA, and that sort of started a group going, which has grown all the way up to this year. So we've got Lydia Corey here, who joined us several years ago, and then Catherine Bloom, a grad student working with Brad, who's at another conference, but she does some very interesting work on Rossby waves and inertial modes. Rafa Fuentes, who we heard from yesterday, Bashek Manek started hanging out with us. He knew Lydia from grad school, so he started walking across campus to come to our group meetings. Then a couple of years ago, Whitney Powers started working with Brad as a student. And Adrian Frazier, who actually wrote a successful NSF postdoc proposal with Keith as his mentor, has joined us for some time. And then I had actually moved to Swery a couple of years ago, and I've been kind of schlepping back across town to see my good friends here. And I finally hired a few friends to work with me over where I am, so now they have to schlep to see me sometimes too. But just this fall, Kunfe Tuwelda-Biren joined us. He's done a lot of flux transport modeling in the past. Kyle Augustin, who some of you know, who was at CEA for a while and then at Northwestern, so he's back in Boulder now. And then most recently, a graduate student, Abdullah Al-Shafi, he's been coming to our group meetings for a while, and he'll start doing his thesis work with me next month once he finishes his master's thesis. And I would just say that it's a real pleasure to work with these folks. And that would never have been possible if Keith had not made a home for me in the applied math department when I was kind of at a real sort of crossroads in my career. And just a very kind, optimistic guy who I think always really saw the true value in people. And so it's interesting to see all of the things in this workshop that he has touched in some fashion. What I'm going to talk about is a little bit different, but I would say that he has touched the field of solar and stellar physics just by making some space for all of us. And with that, I'm going to kind of move on, but Keith looms large in the background of everything that I want to talk about. So what do I want to actually talk about today? I kind of looked at the schedule, and the speakers and said, I think I'm the solar guy. So I thought, I'll talk as generally as I can about the sun. So I want to talk a little bit about solar magnetism in general, and fluid motions in the sun, and what we know about those, and how we know about those. And so I hope that, if nothing else, if Hal has to cut me off, that I at least get through bullet points 1 and 2, and you walk away just having learned something. And then I want to talk about a particular problem in solar physics right now called the convective conundrum, which is interesting for a variety of reasons, but I think at least that the correct interpretation of this problem really relies on an understanding of rotating convection, which is what we're all here about. So I want to give you kind of one vignette into solar physics where the expertise in this room, I think, could be very useful moving forward. And I think there's a lot of work to do here still. And then at the very end, I'll talk a little bit about some future directions, if I can remember exactly where I'm going or what I'm doing, and which isn't true all the time, but that's why I work in astronomy. Astronomy has a fine history of people doing things that they don't exactly know what it is. Case in point, for quite some time, people were doing something that you're told never, ever, ever to do. and looking at the sun and noting that there are these little dark spots on it. And there are written accounts from nearly 2,000 years ago. And then detailed observations started happening after the invention of the telescope in the early 1600s. This is a nice drawing by Galileo Galilei. You can find these if you search up the Galileo project at Rice University. But I think this is very interesting. Starting around the 1600s, we have very detailed records of the number of sunspots that have appeared on the disk of the sun as a function of time. Let's just ignore this bottom for a minute. Just the main thing to see here are the dates. And so people noticed several hundred years ago that the number of spots would peak and then decline and peak and decline and peak and decline. And here I'm just showing a historical reconstruction, kind of a composite of many different sunspot records that was done in part by the guy next door to me at SORI, Andres Munoz. But what I find so fascinating about this is that no one could have known what they were actually looking at, because we didn't have a robust theory of electromagnetism until 2.5 centuries later. And even then, it wasn't until another 50 years later that the Zeeman effect was something that was understood, and it was actually observed to be taking place inside of a sunspot when Carrington made some observations. And so this is what I mean when I say I think astronomers often do things where they don't really know quite what they're doing. We're always looking, we see things, and there are implications for those things that we see. One thing Galileo did know, or he should have known, if he made a flip book, and I think this is fascinating as well, is that the sun rotates, right? And so if you take his sunspots, let me see if I can go back to the slide there. Hang on, sorry about that. PowerPoint, right? And you take his records from day to day and you play them as a cartoon, you can actually see the rotation of the sun. So even though he could not possibly have had any real idea of what those were, he could have inferred that the sun was rotating. Since Galileo's time, telescopes have come quite a ways. I found this nice composite image in an article on kind of a summary of what we can do with ground-based observations right now. So we have these massive observatories all over the world. And now we have them in space. So this is, as of 2024, everything that NASA's heliophysics division is flying, whether on their own or in collaboration with other divisions or other space agencies. And so all of these are, in some sense, designed to observe the sun or to observe the environment in space around the sun, the heliosphere. But mainly they observe the sun or they observe the magnetosphere around the Earth to try to better understand the effects of this star that's so close to us. Now we know, when we look at these sunspots, that they are magnetic. If you were to look at the disk of the sun, and this shows the Earth to scale, you see these little bubbles out away from the dark area. This is called granulation. This is a type of convection that's driven by radiative cooling at the surface of the sun. We call the surface the photosphere. And then this dark area, which looks dark, it's still actually very hot. So out here where the granulation is, it's something close to 6,000 Kelvin. And we're more like 4,500 Kelvin in these sunspots. So that's why they appear dark on the disk. They're dark in contrast. And what's happened there is that the magnetic field is so strong that it has essentially prevented the convection from taking place. And there's a transition region here where the granulation that doesn't know anything about the magnetism starts to experience a strong overturning magnetic field, and you see the granules stretched out here in this part of the sunspot that we call the penumbra, I think. I always get the umbra and the penumbra a little bit mixed up, but this area. And so this, I think, already illustrates something very interesting about the sun. We've heard so much about asymptotics this week. The difficulty with the sun is that there is no asymptotic sun. There's a place where, in here, for instance, where magnetism dominates everything, and then there's a place out here where magnetism really doesn't matter at all. And there's something in the middle, and they all sit right next to each other. And so trying to model this or understand this can be very challenging. And this is a general theme for the sun, as we'll see as we sort of move through this talk. One thing I like about this just looks like a cartoon, like some theorist. You just draw some stuff. The sun is remarkable for another reason. It's, I think, the only object in the solar system, someone can correct me, where we can actually see the dynamo at work, where we see some of the plasma motions that take part in the dynamo. So what you're seeing here is plasma that has been suspended over magnetic field lines in what we call a coronal arcade, and it looks as though it's raining down. So what's happening is what you're seeing here is plasma that has a temperature of about 50,000 Kelvin, and so it appears in this particular EUV line that was taken by the atmospheric imaging array on SDO. But there's plasma up here that you don't see that's actually much hotter, and it's cooling. And as it cools, it's draining down the magnetic field lines here. And so we don't need anybody to draw a cartoon for us. We can see this taking place. And there's dragons out there too, but we're not going to talk about those today. But these magnetic features on the surface of the sun are particularly interesting to us as a modern society because of these eruptive events that they drive. And over here we're actually seeing a movie from the day when they first turned on the Solar Dynamics Observatory, and there was a prominence that erupted and generated a coronal mass ejection. And these are just masses of charged particles that are flung out when the magnetic tension that is built up somewhere down here is finally released. You can actually see up here, it's a little hard to see on this screen, but you can kind of get a sense of how big these things can become as they expand. You have a bunch of charged particles flying past your satellite, that can be a problem. Past your astronauts, that can be a problem. Can also heat the atmosphere, and so a satellite that was once in space is no longer in space and is experiencing a drag, which can be a problem as well in terms of maintaining altitude. So all of this is of great interest from a practical standpoint, but also from an academic standpoint. So I mentioned before that the sunspot number would sort of grow and diminish and grow again with time. And we know now this is the solar cycle. And so what's happening is that the large-scale dipolar field of the sun is reversing between one of these peaks and the next, and that's about 11 years. And so if you go from one peak to the peak 2 over, so 22 years later, the magnetic field will have undergone a full reversal. And it's still not fully understood why this happens. When sunspots emerge on the disk of the sun, they also exhibit some interesting ordering properties. At the beginning of the cycle, they start to emerge at high latitudes, and over the course of the cycle, they merge at lower and lower latitudes. So what you're seeing here is called a butterfly diagram. Don't worry so much about the colors, just the idea is that any point on this axis is a point in time, and we just said, okay, where in latitude did we see sunspots that day, and put a dot there, okay? So we've integrated over longitude in some sense. And you can see why it's called a butterfly diagram. But this happens with remarkable regularity. Sunspots tend to emerge in pairs. They have other properties related to their tilt, and which is the leading polarity and which is the trailing polarity. And so all of this really begs the question, where is all this magnetism ultimately coming from, and why is it so ordered in space and time? Right? This is very different from the Earth, for instance, where if we look at the geological record, we see reversals in the Earth, but they seem to be in the Earth's magnetic field, but they seem to be much more chaotic and sporadic. As you probably guessed already, and we'll talk about it more in a minute, but the sun is hot enough that what you actually have there is a plasma, not some inert gas. And so when we're asking where does the magnetism come from, we're really asking something about the induction equation here, right? And this is where rotation becomes important, right? We would like to have some sense of what the characteristic Rossby number of the sun is, and for two reasons. One is just the Rossby number is telling us something about the convective timescale, so it's telling us about the amplitude of U here in the induction equation. But more importantly, it's telling us about the gradients. Right? The structure of the convection is going to depend on the competition between Coriolis and inertial forces in this system. And all of that is going to feed into the EMF right here. Okay? And here's just an illustration. I love to show this. There's John here. Chang. Yeah, I show this all the time. But I usually do it in reverse of what I'm going to do. Here in this crowd, we know this is a given, right? So now I'm just reminding people. In front of some other folks, I say, no, this is real. So we know, of course, right, as we rotate faster and faster, we move from this regime of, 3D turbulence, box-filling convective modes, to things that are much more organized and columnar and helical in nature, right? And I don't think I need to dwell on this with this crowd. But this occurs in models as well. So, here's kind of a schematic of a meridional plane in a sphere, but if you're non-rotating or you're at very high Rossby-number, your convective motions are more or less isotropic. And as you increase the rotation rate or decrease the convective flow speed, you start to develop these Taylor columns or Busa columns that become thinner and thinner as you move to the right. And of course, in the sun, it's going to be a very turbulent system, so it's not like we have these coherent telephone poles poking through the sun. And this manifests in three-dimensional models. And here I've just taken a series of solar convection models at a constant flux Rayleigh number, and I've decreased the Ekman number from left to right. And you see that we're starting to make things less supercritical, of course, but this is a nice illustration that just shows how you can see these columnar structures as you increase the rotation rate in a sphere. Now, at this point, I want to know what the Rossby number is. And so Daniel is going to ask me, come on, you're going to ask me which Rossby number I'm talking about. He's not going to.
I don't even need to anymore. It worked. My strategy worked.
Pat yourself on the back.
But no, what I noticed is John gave a nice talk in the beginning. He said, okay, there is the Rossby number, and there is the convective Rossby number. And then Daniel brought up some other terminology, the input Rossby number and the output Rossby number. And I thought, okay. But then I don't know if anybody noticed, but yesterday afternoon he said, what about the actual Rossby number? And so I got to thinking, we've got an input and an output, and then we've got this black box. And so somewhere in this box, there's truth. And so I looked, and I found it, and it had a little A, and I thought I had learned something, but then I looked around some more, and I thought, I am in the wrong box. So I closed that, and I went on. So whenever I say, what is the Rossby number? All I'm really saying is, what is the characteristic convective flow speed in the deep sun? Take your favorite measure, whether it's vorticity, do you use the system scale, do you use some integral scale? I don't care. I just want to know this. What is the characteristic convective flow speed in the deep sun? So how do we know this? Or how can we at least try to know this? I would argue that if anybody tells you they know it, they're one of those people that just says they know everything, because I don't think we do. Oh, my movie's not playing. Come on now. So if we look at this granulation that I mentioned earlier on the surface of the sun, we see that it's quite dynamic. What you're watching here is a movie that takes place over the course of 1 hour. You're seeing emission in blue light, which they color orange so that it looks like the sun. I was telling Brad this morning, I think that's funny. And this is taken by a telescope on the Canary Islands, La Palma, the Swedish solar telescope. But these little bubbles that you see, the length scale of those is something like 1,000 kilometers, or a megameter. Solar physicists tend to work in megameters, but I'll try to say kilometers. And the time scale of these things is just a few minutes. So this is popping off all the time, all over the surface of the sun. But while this is happening, probably one of the most important processes in all of solar and really stellar physics is also happening. And so we're seeing the photosphere, and you're seeing this emission where things become optically thin and the plasma radiates light. But what's also going on is, as the plasma cools, we form these downflow plumes. And okay, that's convection. Everybody here likes convection. But what's far more important than that is that these downflow plumes create little sound waves. And so this is happening all the time. I was trying on my phone when I couldn't sleep last night, but I couldn't find the paper. But there's a paper, maybe Brad knows, I think it's by Yuri Tomre and Douglas Goff, but it starts out, it says, the sun is ringing like a bell. And this is very true. It's like there's a little sandstorm going on all the time, generating, stochastically generating sound waves. But the sun itself is a resonant acoustic cavity.
So how do you measure that?
How do you measure?
When it's creating sound?
How do we measure? Yeah. So what we do is we use some sort of Doppler interferometer to measure the Doppler shift pixel by pixel on the sun. And so the one that I first became familiar with as a grad student was the Michelson Doppler interferometer that flew on the SOHO spacecraft. And what you had there was an image of the sun that was roughly 1,000 by 1,000 across. So at the center of the sun, 1 pixel was like 1,500 kilometers. So that's kind of the resolution that you have. The radius of the sun is 700,000 kilometers, for some perspective there. And what it would do is it would integrate for a minute, and every minute it would give you what we call a Dopplegram. And that is just giving you, at each pixel, an integer, essentially, that is giving you a sense of the Doppler shift and whether it's positive or negative. And if you were to view this over time, maybe pick a little patch, this is what you would see. And so what you're seeing is sort of I'm trying to think of the word, you're seeing a whole spectrum of interfering sound waves right here. So the whole surface of the sun is bouncing up and down very, very lightly, but all the time. And if you were to look at the full sphere and decompose these into full spherical harmonics, what we call global modes, what you see are these ridges that pop out in the Fourier transform. So here I've got frequency on the y-axis. You see a lot of power here around 3 millihertz, which is around 5 minutes, which is similar to the time scale that you're forcing the system at with this small scale granulation. And on the x-axis, we've got things, the spherical harmonic degree. And I believe this particular image, the power has been integrated over m's. So at a given L, you're seeing all the power from all the m's. But the idea is that these different ridges are telling us different things. This low ridge that you can see here just barely, these are actually surface gravity waves. And so those modes are sampling the surface layers of the sun, kind of roughly a depth that's commensurate with the granulation that I showed you. So I think a megameter and a half or so, something like that. And then each of these ridges are sound. They correspond to sound waves that have a different number of radial nodes in radius. And the really high wave number stuff tends to kind of skip and sample the surface layers, like on this little plot here. And the really low wave number stuff tends to penetrate much more deeply into the sun. And so if we look at how the frequencies of these different modes are perturbed, we can infer through inversions something about the flow or other properties of the sun. And yes?
Is it possible to superpose the dispersion relation for sound waves? I can see it,
I certainly could. I don't have it. I can't do it now, if that's what you're asking. I mean, the dispersion relation, it looks like this. I don't mean that facetiously. I mean, it's each of these ridges corresponds to a particular mode of sound wave. This mode has, is this 1 or 0 nodes in radius, Brad? I forget. Is this P0? Yeah. And then this ridge would have 2 nodes in radius. Yeah. But I don't have the dispersion relation. I'm sorry. So there are 2 big results from helioseismology, and then lots of other interesting results. But there are 2 that I would say that are pretty much inarguable at this point. And the first one is that we have a very good sense now of the sun's thermal structure. We know that something like the outer 1/3 by radius is convectively unstable. We have a sense of the run of temperature and density across this region. And we know that below that radius, photon diffusion is very efficient. And so the photons are scattering throughout the system. Fun fact, if you ever want to tell somebody, is, when you see light from the sun, it spent something on average like 100,000 years bouncing around in here before it gets to the convection zone. And then somewhere between a month and a year later, that energy makes its way to the surface and things cool and it dies undramatically on your eyeball. So what do we know about the structure of the sun? The thermal structure first. So all of this interesting stuff that we see at the photosphere is taking place over a depth that's something like 1,000 kilometers. You can decide where you want to draw this line. But it would be thinner than the line that I used to just draw this little schematic of the convection zone here. And the temperature and the density vary fairly dramatically even across this little region, right? You're getting a 3-fold change in temperature and something like a 10-fold change in the density right there. But the region that most of us in this room are probably most interested with is the bulk of this convection zone. And here things vary even quite a bit more. So you go from a temperature of around 10,000 to a temperature of around 2 million Kelvin at the base. And the density varies quite dramatically by a factor of about 10 to the 5. And so what all of this translates to is that across this region, there are something like 11 density scale heights. If you were to calculate a Reynolds number or a Rayleigh number or any of these non-dimensional numbers, they're just really big or really small. They're so big and they're so small that no matter how hard we try, it's still hard to do a bad job when we model this system, right? We're all trying to do a bad job, and we can't even do that. I think that's something kind of take home. The other big thing that we get out of helioseismology is a sense of the fluid motions in the sun. The main result that is sort of a cornerstone of solar physics is that we know the internal differential rotation. We know that the sun has a rapidly rotating equator and slowly rotating poles. The sun rotates once every 24 days at the equator and about once every 30 days at the pole, with an average rate of period of about 27 days. And there's also so we have all of this shear and latitude from the differential rotation, but there's two other shear layers of interest, and they're not, I need to use this figure just has nice color. I need to find a better one next time though. But the first is the near surface shear layer. So you see these contours of constant angular velocity starting to bend as you approach the surface. So in the outer 15% of the convection zone, the shear that is established diminishes fairly substantially. And we don't know why that is, and we don't know if this plays a role in the dynamo or not. And then at the base, everything transitions to nearly solid body rotation in a region that we call the tachocline. And we're starting, I think, to get a handle on that, how this occurs. And in fact, Lauren Matilski is over here somewhere. He's going to speak on this on Friday. The differential rotation is very well measured because it is symmetric in the north and the south. And so these global scale modes that I talked about are able to sample that. The problem is that those modes sample symmetrically in the northern and southern hemispheres. So if we want to look at flows that are not symmetric, we have to use little patches of the sun and look at local plane waves, but they don't sample as deeply. And so the kind of companion flow to the differential rotation is the large-scale meridional circulation. And at the surface, we know that it's poleward, but where the return flow occurs at depth and whether or not there are multiple cells in depth is still up for quite a bit of debate. And so some measurement techniques and some instruments seem to show that there are no counter cells in depth, whereas others show many counter cells. So here you see northward flow switching to southward, switching back to northward. But over here, there's northward and then just a very deep southward return flow. All of this is important, of course, because if we have shear, we can stretch out magnetic field lines, create new magnetic field. So we think that's a big contribution of the differential rotation. This lends itself often to something known as an interface dynamo. So we have shear in the convection zone, but then we have all of this shear in the tachocline. So the idea is that maybe convective downdrafts are pumping magnetic field into the tachocline, where this shearing helps to strengthen the field and also organize it, and eventually it becomes buoyant and rises to the surface. This is what's called an interface dynamo. Sometimes these interface dynamo models operate in tandem with a meridional flow that is helping to set the timing of the cycle. And so this is kind of just showing little toroidal belts of magnetic field that are being advected along with the meridional flow over the course of the cycle. But there are other possibilities, and that's that we don't need any kind of meridional flow, that it's not a flux transport process. Maybe we don't even need a tachocline. This is some work done by Ben Brown during his thesis, and he found that in certain situations, which are generally low Rossby number, you can develop very coherent magnetic structures that kind of encircle the equator. And so you're seeing kind of the equatorial region here. And blue is one polarity and red is another polarity. And if you run the model long enough, these can actually flip. And there's no really coherent meridional flow. There's no tachocline in these models. And this feature is observed in quite a number of dynamo models and has been since 2009, 2010, and is today. So pretty much any model that cycles has something like this in it. And they tend to happen at a relatively low fluid Rossby number. And for the sun, this number would translate to an interior flow speed of something like 30 meters a second. Okay. All right, so we'd like to know what the flow is in the sun. So why don't we have a look? So if we take the velocity spectrum at the solar surface and just look at the power as a function of spherical harmonic degree, we see a couple of things. First is this very prominent peak, and this comes from the center of the disk. This is due to all of this granulation that we saw. It's primarily radial motion. It's popping off every few minutes or so. And then we see another peak, and this contribution to the spectrum is what we're probably most interested in here, and this comes from the limb. And so here, you're seeing motion that's not associated with the radiative cooling, but it's some larger scale motion. And because you see it on the limb, while it's line of sight motion, it's predominantly horizontal. So here we're seeing some much larger scale overturning motion. That we call that supergranulation. We'll talk about that in a moment. But what we don't see is any significant power out at the box scale. And for folks who don't think in terms of rotating convection, I think this has been a big surprise for a very long time, right? Because in our head, we expect to see power. You know, we've got this bump. We can understand this bump being kind of out of place because we're really seeing two components of two different flows. So if we ignore this, we might expect power to rise and keep rising until we reach some scale commensurate with the depth of the convection zone, which is around L of 10, somewhere over there. And we don't see that, and that's been a big mystery. We do see flows out there. This is some helioseismic analysis, just showing flow field on what we call a synoptic map. So you're seeing latitude and longitude. There's nothing particularly special for this talk that's different about the top or the bottom. These are two different time periods. And so we see these meandering flows, but they're not very cellular, and they're not that strong. They're not going to give us this peak out there. So even if we look a little bit below the surface, we don't see that. And people have been trying for a very long time to see large-scale flows at some depth in the sun to understand where are these so-called giant cells, these convective motions that nominally fill the convective layer. And if we compare many different observation techniques, we see that there are disagreement even among observations. Now, there's some models that are put on here, and I really don't care about those. Models are models, but observations are observations. And these techniques do not agree yet. This recent work led by Aaron Birch took an older version of this plot and managed to bring things back into better agreement. But there's still some question of why, for instance, ring diagram, helioseismology, two different versions don't agree with one another. And then time distance techniques say we don't even see anything. We can just provide an upper limit on what the flows might be. And some of this is a little confusing because these measurements are taken at slightly different depths, but that's actually kind of a detail in this context. And I would say the general picture is that we don't know. There appears to be a lack of large-scale power, and is this puzzling or not? What we do see at the surface is this stuff called supergranulation. And so what supergranulation does is, among other things, is it tends to advect magnetic field to the boundaries of these convective cells. And the magnetic field acts like little fiber optics poking down to a slightly hotter region of the sun. And so it traces in these little light bits the boundaries of the supergranule. So don't focus on these big bright regions, but look somewhere away from them. And there's a certain spatial scale that your eye picks out, and that's supergranulation. And we can measure these flows. We know their spatial scale. And if you say, what's a Rossby number for those, it comes out to around 3. So these flows, whatever they are not rotationally constrained. Yes?
Rossby number of 3, that's with that length scale and the flow velocity
That
at
is
the
right.
surface.
That is correct. Yes, I'm using these numbers to create and the solar rotation rate to create a Rossby number. So,
But if those features went further down,
if they went further
velocities would
down,
change then.
yeah. But if they went further down, you'd probably, well, you know, I'm not even. The answer to your question is that, yeah. Sorry, I just saw my stopwatch here. So, but we know that the Rossby number is very important for solar differential rotation, and a very robust result is that if you run a system with a convective Rossby number less than 1, you will generate a differential rotation that roughly resembles that of the sun in the sense that you have a rapidly rotating equator and slowly rotating poles. But if you move into the other regime where your convective Rossby is greater than 1, so Coriolis forces are not important, then you see something that's the opposite of the sun, which we tend to call anti-solar differential rotation. Of course, we know what the sun is doing, and so at the surface we see this supergranulation that acts like a high Rossby flow, but the bulk of the convection zone is behaving like a low Rossby number flow. And we know also, I should say, that part of the only way I know of to get this sort of flow is to have some kind of correlations like you see in these columns where there's an organized tilt to the columns, and that is what helps you establish this anisotropy in the angular momentum transport. Okay. I'm actually doing okay on the time. So just kind of in summary, what might we expect to see at the solar surface? So we know that the convection we see is high Rossby number. We've got these granular motions that are something like kilometers a second. Supergranulation, which is 400 meters per second. Those are both too fast for the Coriolis force to matter. But we know that the deep is acting like a low Rossby number flow. And so the sun must exhibit some kind of Rossby number transition with depth. And so if you want to apply, for instance, asymptotics to the sun, you might do well down here, but you're going to do really poorly up here. But what might be the consequence of this? So I would say that the picture a lot of solar physicists have had in their head for several years is something where there is some kind of motion that's filling the box, and that's a deep-seated motion, and it's, acting alongside, it contributes to a net power spectrum that's also comprised of these near-surface supergranular motions like I've sketched here in red. And so the spectrum we see at the surface should look like some combination of those two things. And this is, I think, what's been expected for a while. Once people started running models, a lot of the first models that showed differential rotation, well before you could even run dynamo models to any useful extent, they would develop columns, and the width of the columns was also essentially the depth of the convection zone. And so the cartoon picture in our head was something like this, but the net result of the power spectrum we expected was the same. It was unchanged in effect. I see the time. I've got it here. 44 minutes, right? But what if the deep convection were even slower than that? Then what would you expect? I mean, if you've ever run a convection model, non-rotating convection models are kind of fun to run. And if you look at the surface, you see the box mode, and it's just sweeping the little tiny cells along everywhere, and you see it. It's just moving these things around. They move in this larger river that's established. But what if it were the other way around? What if things were so weak at depth that, in fact, you had these very tiny structures that are maybe columnar or coherent on very small spatial scales? It's a lot harder to imagine how that's going to manifest as some sweeping around of this rapid stuff that's popping off every couple of days versus things here that might live for a few months. And what would the power spectrum look like? And it's possible, this is very much cartoon physics, that you could reproduce a power spectrum that looks something like what we see with supergranulation. It's not that we're missing the giant cell power for some reason. It's that it doesn't exist because the sun is operating in a lower Rossby-number regime than has been expected traditionally. And so then you can ask yourself, well, how slow does the deep motion need to be in order to achieve something like this? Another way to say that is, how slow does the deep motion need to be so that these cells are roughly the size of supergranules, so that your characteristic length scale is like L of 100 instead of L of 10? And you can run this with numerical models, and you come out with a number that's around 10 meters per second as sort of RMS, characteristic flow speed. And this is done with 3D numerical models. It's been done in 2 different efforts by our group in spherical models, and then more recently, Peter Capula published a paper. In fact, I don't think that's Capula at all. I apologize. I think that's just Capula. And he found a similar number, though he doesn't agree with this cartoon at all, but he's not here talking, so. But that's a fairly robust result. That's roughly the flow speed that you need. What's interesting is that if you just look at supergranules, you actually see that at the base, it's around 10 meters per second. So they're hitting a number that is rotationally constrained at their base. I'm going to skip that for time. Sorry, I don't know what it's not. Another fun exercise you can do is you can say, well, what if I say, what might a convective Rossby number be based on what I can see in the system? And so here I didn't write it in terms of Rayleigh and Ekman. I wrote it in terms of the actual system parameters. And in order to carry out this exercise, what you need to know is something about the solar structure. So we've got the background temperature and the gravitational acceleration, the depth. And then we ask, what temperature perturbation should we use? What T prime? There's some guidance on that, both from intensity variations across supergranulation and also looking at pole to equator emissivity, so larger scale variations. It's all around a Kelvin. And if you put that in and then say, what does this convective Rossby number map out to? You get 0.178. What does that map to in a nonlinear simulation? It's about 27 meters per second. So it's order 10 meters per second. Much more recently, this just came up on the archive the other day. Sasha Brun and collaborators, in fact, this is run by is this a student or postdoc? Noraz? Postdoc at CEA. And they managed to run a model that has a really high degree of density stratification. 6 density scale heights, which is tough to do in a sphere, okay? And what they are starting to see are small scale structures at the surface where you don't really see the imprint of columnar convection and columns down below. So very interesting paper that I've only just started to read. I was just pointing to it the other day. So there might be the beginnings of some numerical support for this idea. And now I just want to, I'm closing up here, Hal. I'm getting there. 2 minutes, right? So I want to move forward for a little bit, though. Again, what might be interesting to this crowd? People are starting to think quite a bit about the poles of the sun. What do the flows look like there? What kind of waves do we see there? A few years ago, let me play this again. What you're seeing is the flow sampled over the course of a year, and it's been mapped back to the polar region, but there's a lot of foreshortening up here. And the sampling scale is something like the size of supergranulation, so it's not very well resolved. But the idea is you're tracking these supergranules, and you say, what are you seeing at the poles? We see something that looks like a polar vortex. It's a very, very interesting structure, and this cutout is where even doing the best that you can from the ecliptic, you just can't see there, and really I don't know how much you trust this stuff, but the general motion on these large scales you do. And this was recently identified as being inertial modes in the sun. And so these are waves where the Coriolis force is, the restoring force. Inertial modes, high latitude inertial modes, equatorial Rossby waves. There's a whole zoo of waves that have just recently become to be known on the sun. And we're just starting to think about how these can be used as an alternative probe of the interior. We use sound waves to do this all the time. Could we use these? So one of partly because of some of that work I just showed, one of the things that came out of the decadal survey in solar and space physics, which was just published this fall, is that the highest priority space mission for the next 10 years is to develop a solar polar orbiter. And a few of us in this room were involved heavily in an initial attempt at this, but it was almost a blessing, I think, that that didn't go, because we were trying to cram too much into a small box, in essence. And in fact, for the one that we proposed, we had to axe the coronagraph, which caused a lot of angst. But the idea is that we would send a satellite out, a probe that has an EUV imager, and a coronagraph, and a magnetodopplergraph. So with that in particular, we can take Doppler measurements of the sun and magnetic field measurements of the sun. We fly out to Jupiter and use Jupiter for a gravity assist to get out of the ecliptic. This has only been done one time before with one of the Ulysses spacecraft, and they de-scoped the imager on that one. So this will be the first time an imager of any sort has flown over the poles of the sun. And if you, in the worst case scenario, where you kind of get one orbit, you'd have 3 months over each pole. But there are ways to use Venus or Earth to tighten up the orbit so that then you don't have, I forget what this time is, it's pretty long to go out to orbit Jupiter and the sun and come back. But you can tighten this up to something that's like 3 years, I think. And so the proposal from the decadal survey is that this begins to be planned in about 5 years from now, so sort of halfway through the decade. And then I'll just close, is it moving, with this. So I did want to show something from our group. This is my final slide. But I think one of the interesting things we can do as a community now is to start to provide some input on what might be seen in the polar regions of the sun in different circumstances. So for instance, if helioseismically we were able to peer beneath this layer of granulation and supergranulation and see some sort of characteristic spatial scale of the convection, that is in turn telling us a lot about the convective flow speed, it's telling us about the underlying structure, and it's telling us quite a bit about the dynamo mechanisms that are likely to be at work in the sun. And so this is just some illustration of some work that we're writing up now, where we ran models at many different convective Rossby numbers. In this case, they vary by a factor of 8 from left to right. And so you can see in these movies that the stuff on the left is almost static, right? It's hardly moving, this very low Rossby number flow. And whereas over here, so by the way, this convective Rossby number is like 1/16, if anybody cares. And over here, it's about a half. And things are much more dynamic. You see much more vortical motions. If you were viewing this thing for 3 months, it would probably look almost like a static flow from the standpoint of a polar imager, whereas something that's much more dynamic would not look that way at all. So I think there's a lot to do, and thanks for letting me go 3 minutes over. Sorry about that. But thank you all very much.